in listen-only mode.
Greetings, everyone. Thank you for attending our webinar today. I'm Corey Guker, coordinator for the Northern Rockies Fire Science Network. And on behalf of our team and our partners, I want to welcome you to today's webinar titled Resilience and Regeneration After Wildfire in Dry Mixed Conifer Forests of the US Northern Rockies. This is going to be presented to you by Kerry Kemp. She's a Ph.D. candidate with the University of Idaho. But before I introduce you to Kerry a little better, I want to just go over a couple of webinar housekeeping items. You can ask questions of our presenter or me anytime during the webinar by typing them into the questions pane of your control panel. That's at the right-hand side of your screen. And I'll keep the questions for Kerry and just field them after the presentation. And just know that anything you do in your control panel or with your own audio doesn't affect the webinar. So feel free to test messaging or your audio anytime. Kerry Kemp is a PhD candidate at the College of Natural Resources at the University of Idaho. Her research focuses on understanding patterns of forest regeneration across environmental gradients after large mixed-severity wildfires in dry mixed conifer forests of the inland Northwest. She's especially interested in how fire mediates vegetation change in response to climate and forest resilience in the face of changing wildfire regimes and altered stand structure from past management practices. Kerry has a BA in Ecology and Evolutionary Biology from the University of Colorado Boulder. Before starting graduate school, she participated in research with the U.S. Forest Service on sudden aspen decline in Colorado and on fire suppression impacts on forest structure in the central Sierra Nevada mountains. While not working on her dissertation, Kerry loves skiing, backpacking, and spending time in the mountains. Welcome, Kerry, and thank you for being here today.
All right, thank you, Corey, and good morning to everyone. Thank you for listening in. So like Corey mentioned, I'm a PhD candidate at the University of Idaho in the Department of Forest, Rangeland, and Fire Sciences. And I work with Drs. Penny Morgan and Phil Higuera. Today I'll be presenting a portion of my dissertation research that's focused on post-fire regeneration in dry mixed conifer forests of the Northern Rockies. And this portion of my research is currently in review in ecological applications. So just to start, in recent decades, the western U.S. has been experiencing an increase in the frequency of large fires, and the largest wildfires, so those exceeding the 90th percentile in size, are continuing to burn more area. So this trend is being driven in part by fires in the U.S. Northern Rockies region, where we've seen large fires that have burned in 1996, 2000, 2007, and then most recently, 2012. So in the Northern Rockies, there's a correlation between warm, dry springs and warm early summers and fire occurrence. Furthermore, work by Westerling et al. In 2006, which I'm sure most people are familiar with, demonstrated a correlation between warm spring temperatures, earlier spring snowmelt, and fire occurrence. And this was especially true in the Northern Rockies region, which you can see highlighted in this map in the orange in central Idaho and Montana. So as we continue to get earlier snowmelt and warmer spring temperatures, the Northern Rockies in particular will be vulnerable to more fires. So we know that large disturbances, and fire especially, are important to the structure and function of ecosystems over decades to centuries. So changes to the disturbance regime, such as a change in their frequency, size, or intensity, can influence the resilience of a system. And here we define ecosystem resilience as the ability of a system to absorb disturbance without changing to a qualitatively different state. So we often use a ball and cup model to conceptualize this concept. So for example, we have a system that exists in some quote-unquote equilibrium state. A disturbance occurs, and that shifts the system out of its current state towards some ecological threshold. So following the disturbance, the system can either return to its initial state, or if that ecological threshold is exceeded, it can shift into a new state. So in the case of a forested system, this new state could be non-forested vegetation, such as persistent shrub fields, or a shift to a different species assemblage entirely, so maybe a shift from conifer dominance to deciduous dominance. So when we talk about forest resilience, we can measure it in two ways. And you have to have essentially some baseline in which to measure forest resilience. So in our case, this baseline is just the pre-fire forest. And so we think about forest resilience in these two different ways. So are trees regenerating where they existed prior to the fire? And does the species composition remain the same? So the resilience of forests to larger and more frequent fires has been especially of a concern in these dry mixed conifer forests in the western U.S., where a legacy of past management activities, including grazing, logging, and fire suppression, have resulted in these changes to species composition, and especially a lot of infilling by these more shade-tolerant species, which have increased stand densities and increased fuel loads. So the traditional paradigm in dry mixed conifer forests of the western U.S., which has been adopted in part from southwestern ponderosa pine-dominated forests, is of these widely spaced open forests that burn relatively frequently. And when they do, fires in these forests tend to be of low intensity and low severity. So naturally, when there's an increase in fuel loading from decades of past management, current fires, when they start burning, are burning more intensely and having more severe post-fire effects. And this increase in burn severity has actually been documented in the southwest U.S. over the past 25 years. So because these forests are not really well adapted to intense high-severity fire, we would expect to see a decrease in forest recovery and resilience following these recent large wildfires in these areas. In dry mixed conifer forests in the Northern Rockies, however, the story isn't quite as straightforward. So these forests are dominated by a mix of different species, and there's evidence that suggests that the fire regimes in these forests vary from frequent low-severity fires at the lowest elevations to more mixed-severity fire regimes in more mesic locations or at higher elevations within this cover type. So furthermore, the fire regimes in these forests can vary on millennial timescales depending on shifts in climate. So we tend to see more low-severity frequent events during cooler periods in the past, and more high-severity events during warmer periods in the past. So although there has been a documented increase in fuel loadings in dry mixed conifer forests in the Northern Rockies due to fire exclusion and historic logging, this hasn't necessarily corresponded to an increase in fire intensity or severity over the past 25 years. So in terms of the resilience of these forests to large fires, we're not really sure how resilient they will be. And the alternative scenario to the one that I presented for the Southwest is that the spatial heterogeneity that we see present in the fires that burn in these forests and the diversity of different species will allow for forest recovery and resilience to fire. So our objective with this study was to quantify the patterns of post-fire regeneration after recent large fire events, with the idea that we would sample across the range of different post-fire and environmental conditions of dry mixed-conifer forests in the Northern Rockies region. And by identifying the mechanisms that influence seedling regeneration at broad scales, we're hoping to get a better understanding of how large fires impact ecosystem resilience and how these forests will recover from these events in the future. So in order to examine patterns of post-fire recovery across the range of different conditions that typify dry mixed-conifer forests in the Northern Rockies, we sampled within 21 large fire events on 6 different national forests across Idaho and Montana. These fire events occurred in the regional fire years of 2000 and 2007. And we specifically chose to sample in these particular years because they were extreme fire years where fires burned across the entire region. And they're likely to be more representative of the burning conditions that we might see in the future. So we had 182 sites which were stratified across a gradient in burn severity, elevation, latitude, and aspect, and specifically they were on northeast and southwest facing slopes to obtain the greatest contrast in incoming solar radiation and heat loading on those sites. And by stratifying the sites in this way, we were able to represent the large majority of different climates that characterize these forests. So just to illustrate this, in the panel below the map on the left side of the screen, the gray block spot represents the ratio of actual to potential evapotranspiration for dry mixed-conifer forests as a whole. So this represents the climate of these forests as a whole. And the white box plot represents this climate variable for our particular sites. So we were able to do a pretty good job of capturing the range of variability of different climates present in these forests across the Northern Rockies. So also, our sampling design was informed by our desire to locate some possible locations on the landscape where the resilience of these forests might be altered due to disturbance. So in particular, if some locations on the landscape were less likely to be resilient to fire, we hypothesized them to have higher burn severity, where the post-fire microenvironment could be altered or seed sources could be eliminated. We also hypothesized them to be in larger burned patches where there's isolation of live seed sources that limits seed dispersal. And on drier south-facing slopes and at lower elevations where the climate conditions now might not be as conducive to reestablishment as they were when the mature trees that burned in the fire established there decades to centuries ago. So at each site, we measured seedling densities on a variable width 60-meter transect that was between a ½ meter and 5 meters on each side. We field verified burn severity from the monitoring trends and burn severity data set. We recorded elevation, aspect, slope, and latitude on each site. We characterized the distance to the nearest live seed source by measuring the 10 nearest live seed trees with a laser rangefinder, which had a range up to 500 meters. We also quantified stand basal area of living and dead trees on 3 variable radius plots along the transect, and then measured understory vegetation cover in 1 meter square quadrats and canopy cover at 3 locations along the transect at 0, 30, and 60 meters. We derived time since fire from the MTBS data for any of the unburned sites, so we ensured that they had been unburned since the recording of began in 1984. And then transformed aspect, slope, and latitude into a heat load index, which is a measure of the amount of solar radiation that a particular site receives. So in general, we found a lot of seedlings across all our sites, and regeneration was really dominated by Douglas fir. Out of the 182 sites that we sampled, roughly 15% had no seedlings. And although we didn't have data on species composition pre-fire, we were able to reconstruct to the best of our ability the species composition of the mature trees prior to the fire by measuring and identifying these trees post-fire. And so what we saw is that the relative proportions of species represented by mature trees pre-fire compared to seedlings post-fire stayed relatively constant across all our sites for all the species that we found. We also did some exploratory data analysis looking at seedling densities as a function of many of our different predictor variables. And we immediately noticed this striking pattern between seedling density and distance to seed source. So specifically, beyond about 150 meters from a live seed source, all the sites had either no or very low regeneration. And in the panel on the right, we have 9 sites that didn't have any seed sources within that 500-meter range of the laser rangefinder. And only one of those sites had seedlings present, which happened to be all lodgepole pine. So when live seed sources are far from a site, seedlings tend to be absent. When seed sources are close, there's a lot of variability in seedling densities. So this led us to wonder if the processes that determine how abundant seedlings are post-fire are different from those that determine whether or not seedlings are present or absent. So to begin to get at this question, we used some logistic regression and exponential count models to examine which of the variables we measured and derived on each site influenced seedling regeneration. And I don't want to belabor this too much, but just to step through the modeling process, we start with a common disturbance occurring at a site, and then we can ask, are seedlings present or absent at that site? So to do this, we use a logistic regression model with a binary distribution where sites that have seedlings present are represented by a 1, and sites with seedlings absent are represented by a 0. So we did this for all of our species, and then because we were interested in whether there were different processes that were important for different species, we separated our models by the 4 most common species on our sites. And in this case, seedling presence is only indicated by a 1 if that species is present on that particular site. Then we want to know, if seedlings are present, how many are there? So for the second part, we used generalized linear regression models with a negative binomial distribution. And because several of our species, in particular lodgepole pine and grand fir, were only present on about 15% of the sites, they had an excess of zeros, and so they were best represented by 0 inflated negative binomial models. So I'll start by sharing the results of the logistic regression models. So for the all-species model, the most influential variable on seedling presence out of all the variables we measured was distance to seed source. So this graph on the left shows the functional relationship between distance to seed source on the x-axis and the probability of seedling presence on the y-axis, while holding all the other variables in the model constant. And since the statistical model we use predicts a binary outcome, which is presence or absence, we can identify a threshold probability that does the best job of separating out these two outcomes. And depending on the nature of the input data, this value can vary, where the probability of 0.5 doesn't always, or isn't always the best predictor of presence or absences. So for our all-species model, this optimal threshold probability corresponded to a distance of roughly 95 meters from the live seed source. So beyond this distance, the seedlings were unlikely to be present. Stand basal area was also an important factor determining seedling presence, and we interpret stand basal area here as a proxy for site productivity. So sites with a stand basal area of above roughly 5 meters squared per hectare had a high probability of seedling reestablishment. Relative to distance to seed source, however, stand basal area really only had a minor influence on seedling establishment. So distance to seed source also seemed to be the overriding factor determining the presence of several of our species. So Douglas fir in the dark green line, ponderosa pine in the light green line, and grand fir in the dark blue. However, distance to seed source wasn't important for the reestablishment of lodgepole pine. And this makes sense based on the biology of the species. Douglas fir and ponderosa pine are heavy-seeded species that don't really disperse far from the live seed source. Lodgepole pine, on the other hand, can exhibit seropony, making it the only species of the four that doesn't depend on a live seed source for regeneration. So using the same method that I described on the previous slide, we were able to identify threshold probabilities for each of these species-specific models that best predicted seedling presence. So these thresholds corresponded to roughly 60 meters from a live seed source for ponderosa pine, 75 meters from a live seed source for Douglas fir, and 165 meters from a live seed source for grand fir. So distance to seed source, as we expected, was the main factor determining seedling presence. Now we want to look at seedling abundance. So to do this, we used negative binomial count models. And getting back to the question I posed initially with the models, we can examine whether there were differences in the variables, which are listed here in the left-hand column of the table, that determine seedling presence versus those that determine seedling abundance. So these numbers are the parameter estimates from the model, which are essentially equivalent to the slope coefficients for each of the variables. And we listed the parameter estimates for any significant variables and omitted them for non-significant variables. So for the all-species model, distance to seed source still appears to be the overriding variable influencing both seedling presence and seedling abundance post-fire. When we look at Douglas fir, however, there are a few variables that appear in the count models that didn't appear in the binary model, namely burn severity and time since fire. So we can think about the influence of these parameter estimates or these factors on seedling abundance by looking at the directionality of the parameter estimates. So for example, there's a positive relationship with time since fire. So the longer time it's been since a site burned, the more Douglas fir seedlings present on that site. A negative relationship with heat load index indicates that there are fewer seedlings, and the probability of finding Douglas fir seedlings is lower on sites with a higher heat load index, which are these warmer, drier sites. The abundance of ponderosa pine seemed to be determined by the same factors that influenced its presence, so namely distance to a live seed source. And for lodgepole pine, there were a couple of variables that determined suitable habitat, so elevation and heat load index. And those were important for determining its presence on a site, but they didn't matter so much for its abundance. So it's likely that some variables that we didn't measure, such as the percent serotiny in a particular stand, had a larger influence on lodgepole abundance. And finally, distance to a live seed source didn't matter for the abundance of grand fir on the site. We hypothesized that this is probably because grand fir seeds tend to be fairly ubiquitous whenever they're present. However, site productivity and vegetation cover had a negative relationship with grand fir abundance, which suggests that there might be some competitive exclusion of seedlings by other shrubs or herbaceous species. So thinking back to the beginning of the presentation, we identified some locations on the landscape that we expected to be less resilient to fire and have lower regeneration. So of those, topography was an important factor for some of the species, so in particular for Douglas fir and lodgepole pine, where regeneration of these species was higher in these cooler, wetter sites and at higher elevations. However, topography wasn't as important of a driver as we hypothesized initially, and it wasn't really a major factor in limiting regeneration in dry mixed conifer forest across our broad study region. So what about burn severity? Well, burn severity was also not as important as we originally hypothesized. So it wasn't a significant factor in any of the binary logistic models that predict seedling presence or absence. And it only appears once in the count models. So what's going on here with burn severity? There's really a lot of focus on the burn severity of a fire event as a driver of ecological change. And we acknowledge that burn severity is likely to be an important driver of many different attributes of the landscape after the fire and affect the post-fire community. But what our work suggests is that the role of burn severity is much more indirect. So in particular, in these dry mixed conifer forests, the mechanism driving seedling establishment is distance to seed source. And high severity sites in particular tend to be further from live seed sources, which makes sense by definition because these sites have higher mortality. So that leaves us with patch size. And given that the distance to a seed source is the overriding variable influencing seedling presence and abundance post-fire, the size and spatial configuration of stand replacing patches becomes the key driver of post-fire recovery. So in order to understand how much of the burn landscape that we sampled in was likely to lack seed sources within these large stand replacing patches, we used the MTBS data for each of our 21 different fire events and found the distance from each high severity pixel to the nearest pixel of lower severity. And what we found was that over 75% of the area burned within these stand replacing patches was within that 95-meter threshold that we identified from the logistic regression. So it was within 95 meters of a lower severity edge. And lower severity edge in this case could be moderately burned, low severity, or unburned. So if we return to our ecological resilience model, we had two measures with which to quantify if dry mixed conifer forests of the Northern Rockies were resilient to these recent large wildfires. And they were, the first one was, are trees regenerating where they existed prior to the fire? And does the species composition remain the same? So in answer to that first question, we know that there are many processes that determine whether or not seedlings will regenerate on a site post-fire, including dispersal, germination, survival, and growth. The models that I presented today mostly speak to the processes of dispersal and germination. So we did sample surviving seedlings, but there were a lot of germinates that we counted, and we know that there's likely a lot of attenuation of those first-year seedlings. But in general, what we found is that if there's a seed source present to disperse seeds onto a site, seedlings will be both present and abundant post-fire. And given that most of the landscape is within the range of live seed sources, we expect that trees will regenerate where they existed prior to the fire. However, where seed sources were available, seedling regeneration was highly variable. And this suggests that seed source is a necessary but actually insufficient explanation of seedling abundance. So once seeds get to a site, they have to germinate, and some of our species-specific models indicate that variables characterizing the suitability of the habitat, such as heat load, elevation, and site productivity, which we again approximated using stand basal area, are likely important for the germination and the abundance of these species on a site where seeds are present. So I do want to note that the fact that these landscape factors don't really negatively influence seedling regeneration in a broad sense across all of our sites suggests that probably much of the landscape where dry mixed conifer forests exist in the Northern Rockies is still suitable for regeneration post-fire. So this brings us to our second question, which was whether the species composition in these sites remain the same. And in general, we didn't see any significant shifts in the proportion of each species represented by mature trees, pre-fire, and seedlings post-fire. So this suggests to us that the mix of burn severities, patch sizes, and environmental conditions that across the landscape perpetuated the stand conditions that were present prior to the fire. However, we do want to acknowledge that post-fire seedling composition at the site scale may still vary as a function of pre-fire species composition and species-specific tree regeneration mechanisms. So in particular, species that don't need a live seed source to regenerate, such as lodgepole pine, may be abundant in stand replacing patches post-fire, depending on the levels of pre-fire surrounding. We also think that the infilling by shade-tolerant species, such as grand fir, in the absence of fire, could alter the seed rain of a patch that's available. Could alter the seed rain that's available to recolonize a patch post-fire. So this, in combination with its potential to disperse up to 2 to 3 times further than either Douglas fir or ponderosa pine, grand fir may become more prolific post-fire as long as seed sources for it are available to recolonize a patch. And this could be especially true in larger patches or in areas where previous logging eliminated some of the mature Douglas fir or ponderosa pine. Okay, so in summary, although there's considerable concern surrounding large fire events in dry mixed conifer forests, what we found is that the diversity of different species and the patch scale heterogeneity present across the burn landscape in the US Northern Rockies suggests that these forests will recover to their pre-disturbance state and that they're highly resilient to large wildfires. We do have a few caveats that we want to note, however, and the first one is that there can't be another fire that occurs before the regenerating seedlings reach reproductive maturity, as this would eliminate seed sources into those patches. The proportion of stand replacing patches can't increase substantially. We haven't seen this in the Northern Rockies in the past 25 years, but that's not to say that it couldn't happen. And finally, climate doesn't shift to the degree that the optimal niche or habitat conditions for seedling establishment become out of sync with where there are seeds available to establish. So the climate for seedlings has to remain favorable. However, in the future, given the potential for more area to burn, we expect that more area will burn severely. So we want to emphasize that it's the size of those severe patches that may determine patterns of post-fire recovery and whether or not these dry mixed conifer forests remain resilient to larger wildfires in the future. So with that, I'd like to acknowledge the help of the many individuals and funding agencies that made this work possible. And at this point, I'll take any questions. Thank you so much for listening.
Thanks, Kerry. We really appreciate you sharing your research with us. Surprisingly, you have one probing question so far. Sean Parks was wondering if you thought about or if you have tried removing distance to a seed source in your models to see if burn severity becomes significant at that point.
That's a really good point. We have not tried that. We tried it the other way. So removing burn severity and leaving in distance to seed source. We went back and forth about that for quite a while, and whether we should even include distance to seeds, or sorry, burn severity in the models at all, because we felt like distance to seed source was really the mechanism that was driving that relationship. So I would anticipate if we took distance to seed source out of the model, that burn severity, and especially the high severity sites, would have a greater influence on those patterns of seedling establishment, just because of that relationship between those high severity sites and that they tend to be further from live seed sources in our data set.
Thanks. There is another question from Vicki Anderson, and she is wondering if you consider differences in soil types as a variable. And she's wondering this especially with respect to fire severity and how that could affect soil changes that affect regeneration and soil types that may change forest characteristics.
Yeah, so we have talked a lot about soil types in our area. So especially the sites in central Idaho are on this kind of decomposed granitic Idaho batholith derived soils that are pretty dry, have low soil moisture. Unfortunately, we did not measure soil type in each of our individual sites, and because these particular models are looking at the site-specific characteristics that we measured in each site, we didn't include a soil variable. However, if we're thinking about doing some additional analysis that's looking more broadly at climate patterns across the region and including broad-scale soil variables in that analysis, because we know that they're likely to be important. So unfortunately, I don't have a good answer about that, but we are going to consider it in future work. So.
Okay. Thanks so much, Kerry. It's really nice to have your information and research out early like this for everyone to get a look at. And it looks like that is all of the questions you got. So I guess you've done a great job of making your case. And I just wanted to let everyone know that there will be a brief 3-question survey will pop up at the end of this webinar, and we'd love for you to provide your feedback. There's also this webinar was recorded, so we'll have a recording will probably be sent to all the attendees, but we'll also post this on our Northern Rockies Fire Science Network website on the past events page. And if you have any more questions regarding this webinar, if you have requests for future webinars, you can call or email me anytime. And thank you all for participating today. And thank you, Kerry, so much. Everyone have a great rest of the day. Thank you.
Thanks, Corey.